All right, this is your stats sensei, Mr. Spensei, and we're going to look at a question 6 that mixes a bunch of different topics on hypothesis tests, but also involves a little bit of regression and just has a very weird ending. And we just kind of want to expose you to that weird ending. So this is a random sample of 400 married couples was selected from a large population of married couples. Heights of married men are approximately normally distributed with a mean of 70 and a standard deviation of 3 inches. That's probably important. Heights of married women are approximately normally distributed with a mean of 65 inches and a standard deviation of 2.5. There were 20 couples in which the wife was taller than her husband, and there were 380 couples in which the wife was shorter than her husband. Find a 95% confidence interval for the proportion of married couples in the population for which the wife is taller than her husband. Interpret your value in the context of this problem. Well, they're asking me to run a one sample proportion, all right? And we know that they're not talking about means and because they don't mention it, but we could make a ratio of 20 over 400, all right? So random sample, they told us was, all right? They told us we had a random sample of 400. And this was a random sample, and I'm just going to make the note of 400. That was given. And need to check the independence condition. 400 divided by 10, there are more than 4,000 married couples, at least before Valentine's. Then we have 20 is our how many couples were where the wife was taller, and 380 or the 400 minus 20. So the sample is large enough to use the normal approximation. So we need to go ahead and run this thing, but we need to figure out what p hat is. P hat is 20 over 400, which is 0.05. So about 5% of the time, the married woman is taller than her husband. So let's go ahead and run this thing. Second vars, excuse me, stat test. One proportion z-test. Oops, keep doing that. Stats test, one proportion z-interval, which is like letter 0 or number 0. Letter A, all right, one proportion z-interval. How many times were they taller? 20 out of 400. And we need to calculate a 95%. So this is our interval. All right, that's our interval. And really what that means is, since it's the confidence interval, the sample mean or p hat will be in the middle, which is 0.05. And then we have a lower and our upper. Our lower is 0.0286 and our upper is 0.0713. We plug in our values, 0.05. This is 0.05 times 0.95. We need to come back and get our, and n is our sample size. Then I need to come back and get our z star. Well, second vars, inverse norm, 1 minus 0.95 divided by 2, because all confidence intervals are 2 tails. And we end up getting 1.96. This is 95% is in here. So that's where the 1.96, and this will be qualified for all of our work shown, and we look really good there. Then it says we need to do our conclusion. We are 95% confident the true population proportion of married couples which the wife is taller than the husband lies within this interval. So somewhere between about 2.8% and 7.1% of couples, the woman is taller than the man. Suppose that a married woman is selected at random and a married man is selected at random. Find the approximate probability the woman will be taller than the man. Wow. So here we kind of have a difficult situation because we're actually combining 2 random variables. So this is one of the more challenging probability. This is a challenging probability problem. And we want that different. So typically men are 5 inches taller than women because this is the average height of men. This is the average height of women. So typically the man is 5 inches taller than the woman. And when we also, since we're working with 2 separate distributions, we have to combine our standard deviations. Well, the standard deviation for the man was 3. The standard deviations for the woman is 2.5. And we can't add those. We cannot just directly add those, and we certainly would never subtract them. Okay, so we have to square them, sum them, then take the square root of that, and that gives us this. So here's what we're working with. On average, the man is 5 inches taller. I need to find out how often the woman is taller, which means I'm going to have to drop down to 0. Okay? So, from this point on, the man is taller going this way. The woman is taller going this way. So this is 4 inches, 3 inches, 2 inches, 1 inch, 0 inches. So 0 inches on, the woman is taller. Anything going this way, the man is taller. So I'm looking for this area. That gives me, I want the probability that Z is less than, based on my graph, 0 minus 5 over my standard deviation. All right. So I can just go to, at this point, second vars, normal CDF, lower bound, negative infinity, upper bound 0, mean, the expected mean was 5 inches, and the standard deviation for the two was 3.9051. And we end up getting 0.100. So in the population, we're expecting 10%. Now I need to show that Z-score. So I can either calculate it by hand, or I could have gone to stat test, and then I could run a Z-test. We had a mean of 5, a standard deviation of 3.9051, 0, and our sample sizes, we're only looking for 1. And we end up with a negative 1.28 for our Z-score, with a probability of that happening of 0.100. So, based on your answers to A and B, are the heights of wives and their husbands independent? The heights of married spouses appear to be related and are not independent. We demonstrated that 10% of married women are taller than married men. However, our confidence interval should have estimated 3% and 7%. Because there is a difference between the two, because 10% is not considered a reasonable, plausible value, to have to lie in here, if it lay in here, we would say, yeah, it might be independent. All right. But since 10% is not contained in it, not independent. So if couple heights were truly independent, the 10% value would have been contained in that confidence interval. All right. Continuing on. D, a scatter plot not shown of husband, and it's like, great. They tell me it's a scatter plot, but they're not going to show me what it is, of a husband's height versus wife height for the 400 men. The sample shows an approximate linear relationship with a correlation of 0.4. On the graph below, sketch an ellipse that would close the points of the scatter plot. Be sure to label your axis and locate and orient your ellipse correctly with respect to the two axes. That is weird. All right, it's kind of a really weird problem. So we have this y equals x line that they gave us. And it's like, okay, how do we get all this information? Well, I plotted height of the wife here and height of the white man there. And remember, married men normally with a mean of 70 and a standard deviation of 3. Oh, well, wait a second. Their mean height is going to be between 60 and 80. So right here at about 70. So that's where the mean height is. the mean height of women is approximately 65. So if it's going to be somewhere, if this is 70 and 65, the mean height for women at 65 is approximately there. Now, what do we know? We know this is a normal distribution, yes? They told us that. So I can go 3 standard deviations below and 3 standard deviations above. 3 standard deviations below 70, my mean height would be at 61. 3 standard deviations above would be at 79. For the women, we had a mean height of 65, standard deviation of 2.5. 3 standard deviations below would be 57.5. 3 standard deviations above would be 72.5. So these lines, these dashed lines, this represented the low for men. That's 3 standard deviations below. This would be the high for men. And this would be the high woman or the tall woman. And these would be the shorter women. Once again, this value is 3 standard deviations below. This is 3 standard deviations above. So I got this intersection. It's like, okay, so this is an intersection, so I need to fit an ellipse in there, and I just kind of sketched it out. And so that would be my ellipse. And that right there would have gotten you full credit. But the trick was recognizing, hey, you know what? This is the normal. This is basically doing the plus or minus 3 standard deviations here and plus or minus 3 standard deviations there. In my personal opinion, everyone should have gotten part A right. Part B is difficult. Some people get it right, some people won't. C, pretty scary. I think a lot of people, I mean, if you don't get B, this was hard to do, all right? So C is a little bit more challenging. D really just required you to put your thinking cap on and go, oh, men's average height's right here, 3 standard deviations below, 3 standard deviations above. Women, 3 standard deviations above, 3 standard deviations below. Not particularly scary, not particularly challenging or hard, but it is challenging because it made you think and they scared you earlier. But this is one where you could have easily gotten part D right. And I think everyone should have gotten part A right. So if you got A and D, you got 2 points. And then if you got B, you're at 3 points. And that's also plausible and probably pretty easy to get a partial credit on part B. Anyway, I appreciate you watching, and I'll see you in the next one.